All right, so welcome to today's webinar. I'm Michael Pfeiffer from Industrial Metallurgists, and today's webinar is on steel hydrogen embrittlement. I'll be talking for about a half hour, maybe a little bit more than that. And at the end of the webinar, there'll be time for questions. I sent out an email a couple hours ago that had the link to the handouts for this, the slides for this webinar. I'm also recording the webinar, and the video will be available to you within a couple of days. You'll have it for a couple of weeks. So that's it. So now, with regards to being speedy, I'll get going with it. I'm going to also turn off my video. Video off. Okay. So I'm Mike Pfeiffer. Just my brief background about myself. I have a bachelor's and master's in metallurgical engineering and a PhD in material science, and I've had over 30 years experience helping companies with metallurgical engineering, helping them with decisions and problems related to the metals used in their products. And that includes product design, manufacturing process development, quality improvement, and failure analysis and root cause analysis. And we also offer on-demand courses, webinars like this, and on-site training. So here are the topics that I'll be covering today. It's what is hydrogen embrittlement, the hydrogen embrittlement mechanism, preventing hydrogen embrittlement, and then I have a failure analysis case study for you. And my focus will be on carbon and low alloy steels. So what is hydrogen embrittlement? Well, it's a type of hydrogen damage due to the presence of atomic hydrogen in steel. That's important. So it's hydrogen that has not joined together with another hydrogen atom to form a hydrogen gas. So it's a single atom of hydrogen, and it results in hydrogen stress cracking, which is fractures at stresses that are less than the metal's yield strength. And this is due to the absorption of hydrogen in the metal. There are other forms of hydrogen damage that cause different problems with the metal, and I won't go into those. There are two broad categories of causes of hydrogen embrittlement. There's internal reversible hydrogen embrittlement, which is hydrogen that's absorbed during fabrication of components. And then there's delayed fracture as a result after the steel absorbs the hydrogen and the parts are exposed to tensile stresses. There's also hydrogen environment embrittlement, and that's due to hydrogen being absorbed during use. So it could be when parts are corroding or exposure like to hydrogen sulfide, where the metal can absorb hydrogen during use. So this slide goes into a little bit about the hydrogen embrittlement mechanism. So hydrogen embrittlement is due to the absorption of hydrogen atoms into a metal, and that the hydrogen atoms are able to diffuse to the grain boundaries where they weaken the grain boundaries. So the hydrogen reduces the cohesive strength between the atoms at the grain boundaries, and as a result, there's cracking at stresses less than the metal's yield strength, because the strength of the grain boundaries has lower strength compared to the strength of the metal itself, or the metal grains. So the fracture mechanism goes like this. We have a steel that's exposed to a tensile stress that exceeds the crack threshold stress. And I'll talk more about threshold stress in a little bit. But for any particular steel that has absorbed some hydrogen, or a particular amount of hydrogen, there will be a crack threshold stress. If the stress the metal is exposed to is above that threshold stress, then cracks will start to form in the metal due to hydrogen embrittlement. And this crack threshold stress is lower than the steel's yield strength. So we have the stress being applied to the metal, and cracks start to form and grow along the grain boundaries. And this is intergranular cracking, and this is due to the hydrogen atoms having diffused to the grain boundaries. So and as the crack grows, the stress on the remaining or the intact material increases, and finally the crack gets large enough, or the intact material gets small enough where the remaining intact material fractures all at once due to overload. So you have, if you look at the fracture surface, what we would see is intergranular cracking combined with overload, but the failure mode is intergranular. The cause of the failure is intergranular cracking due to hydrogen embrittlement. This is referred to as being delayed fracture, where the crack formation and growth involves hydrogen atoms diffusing through the metal to the crack tip. And this diffusion takes time. And as the crack tip grows, more hydrogen diffuses to the tip, and it reduces the metal's strength, and then the crack continues to grow. And here's an example, and I'll be using this example in the case study. These are scanning electron microscope images of a fastener, of the fracture surface of a fastener that failed due to hydrogen embrittlement. The outer portion of the fracture surface had this appearance, which is what we see here is intergranular cracking. So this magnification is at 1,000 times magnification, and in the center portion of the fastener, we have dimple rupture, indicating that the material had been overloaded. So the stress on the material exceeded the material's tensile strength. So the crack grew, and then when the crack grew large enough, the remaining intact material didn't have enough strength, and the material broke. So now I want to talk a little bit about atomic hydrogen absorption. So it can occur during several parts of fabrication. First of all, hydrogen is absorbed during steel making. And even if we just take parts, steel from a steel mill, it will have a small amount of hydrogen in it. And that in itself is not a problem. And I'll talk more about that. Steel can also pick up hydrogen during cleaning processes such as acid pickling and cathodic electrocleaning, and those are used for preparing parts to receive a coating, and then also during coating processes. So during the electroplating process or electrolysis nickel deposition process and phosphating, hydrogen atom, the metal is exposed to hydrogen atoms, and those atoms can be absorbed into the metal. And then also during welding, the metal can absorb hydrogen. During use, we have a steel that is corroding an acid or corroding in neutral water, then part of the reaction involves the formation of hydrogen atoms, which can be absorbed. Also, if a steel is protected by zinc and the zinc corrodes, part of the corrosion reaction will involve formation of hydrogen atoms that can be absorbed. And then in gas and oil, for parts exposed to hydrogen sulfide, that can result in hydrogen absorption as well. So again, the hydrogen is absorbed, and then it can diffuse to the grain boundary. Watch the entire video of the steel hydrogen embrittlement webinar recording at this URL. The URL is also shown in the description for the video that you just watched. In the entire video, you will learn about approaches to use to prevent hydrogen embrittlement of high-strength steel components. Feel free to email or to call if you have any questions. Thanks for watching.